Okay, so the goal for today's lecture is to do decoding concatenated codes. Recall concatenated codes are just this thing in which we have an outer code of an NKD, capital letters NKD over a potentially large alphabet capital Q, and an inner code small n, small k, small d over a smaller alphabet, with the interface between the two alphabets being that the outer alphabet and the inner alphabet have this sort of a relationship. Then we managed to get a concatenated code whose parameters were, which was over the smaller alphabet, but whose block length, dimension, distance, all of them were product of the respective block lengths, dimensions, and the distance of the outer and inner code. And we used this to construct good codes last time. The goal today will be to come up with decoding algorithms for concatenated codes. We'll start off with a vanilla decoding algorithm and see how that itself is very powerful. And then we'll actually come up with a more refined decoding algorithm. So what's the decoding question? So to look at the decoding question, first let's see what the encoding process is. So we have this message, this K symbol message. The outer code decodes it and encodes it, and we get an N symbol message, N symbol code word. Now we are going to apply the inner code word. Independently on each of the blocks. So each of the blocks we're going to apply in the inner code word, Cin. So we got sort of get a y11 all the way up to y1n, y21 all the way up to y2n, and so on, yn1 all the way up to yn. So that's the decoding process. That's the encoding process. Now, what's the decoding question? So in principle, somebody could have this thing goes through a so there's a potentially there's a corruption happening. Say there's a channel. This thing goes through the channel, and there's a corruption that happens. This could be either Shannon's channel, which is randomized, or the Hamming's channel, which worst case errors. And now what you have here is a received word. You get R11, R1n, R21, R2n, Rn1, Rn. Now, how would you expect to decode this? So the decoding question is now the following. Given R11, R1n, R21, R2n, and so on all the way up to Rn1, Rnn. Compute M1, M2. So that's the question. So how would you go about doing this?
Decode each character individually and then
yeah. So let's do the vanilla decoding. So let's do the vanilla decoding, which is the most natural. This one, which is going to be the following. Take this guy. We sort of do first the inner decoding. First we do inner decoding. So we get, say, Z1, Z2, all the way up to Zn. Now, how are the ZIs defined? The ZIs are basically, you could do either a fancy inner decoder, but because the inner decoder is small, you could just run brute force. You could just pick that C inner of Z, so it's the one that's minimum distance to Ri1 up to Ri. Is that okay? So you just pick this. So this you could either use a fancy inner decoder, or right now let's just assume you just using, one can assume you do this using brute force. And then the idea is, of course, to use to an outer decoder to get M1 tilde up to MK tilde. Now use an outer decoder. Inner decoder on each block. That's the most natural thing to do, and let's see what's the performance of this. So once again, is this thing fine? What am I doing over here? I'm taking each inner block separately, applying an inner decoding to get a ZI which is such that the encoding of that ZI is as close as to this R1 to Rn. You could do this based on an inner decoder or just brute force, because the inner decoder is so small enough you could afford to do this. Else, and once we are done this, now you have you have this message, you have this potential message. You're going to now apply outer decoding to get M1 tilde, M2 tilde, all the way up to MK tilde. And the question which we want to ask is, when can we guarantee? What we want to ask is, when can we guarantee M1 tilde, M2 tilde, MK tilde is the same as the original message M1, M2, MK. People with me so far? Sorry, because I don't have my other thing. I don't have a video on, so I don't know. So I need audio feedback.
Yeah.
Okay.
Yes.
So let's try to answer this question. So we'll make a couple of very simple observations. If the number of errors in the ith block is less than d by 2, then what can you say?
Inner decoding.
So then you know that the ith block, whatever you have got the decoded Zi, is in fact equal to Yi. Recall, Yi's are this. So you had this message M, then where the X's, which was, and Yi's are this object. Rather, not Yi is not Zi, but this one is possible. The encoding of Zi is in fact equal to Yi. Or equivalently, that is actually, that will mean that Zi is equal to Xi. Is that okay?
Yeah.
That's claim 1. So this is when, so claim 1 is stating when does the inner decoder work. Now I want to ask, when does the outer decoder work? So is the number of blocks I such that Zi equals Xi, or rather Zi not equal to Xi, if this is less than d by 2, then you are within the unique decoding radius of the outer object, and then you will certainly have that M1, M2, Mk will in fact be equal to M1 tilde, M2 tilde, all the way up to Mk tilde. Is that okay?
Yes.
So if the inner decoding had worked such that at most small d by 2 of them are erroneous, then the outer decoding will work. Now the question is, when does these two things happen together? I want to make the following claim. If the total number of errors is less than d by 2 times d by 2, then number of blocks I with greater than or equal to d by 2 errors in that block is less than d by 2. And do you see that?
Yes.
Because otherwise certainly d by 2, and that's a contradiction, because you assume the total number of errors is less than d by 4. Fair enough. So what does this say? The conclusion of all of this is the vanilla concatenated decoder can correct P errors if, not if, as long if, small if, not can, if P is less than dd by 4. That's the final conclusion we have. Okay, so that's the vanilla decoder, and that does so much. So a couple of things. Why am I calling this the vanilla decoder? Because it's the most obvious thing to do. But notice this is not the best that one should hope for. What's the best that one can hope for? Yeah. Not, so the first thing I want to say is not the best one can hope for, which is dd by 2. Because dd is a bound on the distance that we have for the concatenated codes. Therefore, dd by 2 is you should certainly is an upper bound on the unique decoding radius. So we should be able to correct all the way up to dd by 2. Question is, can we do this? By the end of today's lecture, we will show that this is in fact feasible if the outer has some more additional properties. But prior to that, what we will now see is even this, despite that, even though this is not the best decoder there, despite that, the vanilla decoder is sufficient to get Shannon capacity. This is not the Hamming sort of worst case errors, but Shannon capacity on BSC. And that's what we'll spend the next 20 minutes or so doing. We'll try to show how the vanilla decoder is already powerful enough to do Shannon capacity. Okay. Questions? Questions on the vanilla decoder. We'll now use the vanilla decoder to actually show that on the BSC channel. By the way, this was the original reason why Forney designed concatenation. He wanted to come up with a code that gets Shannon capacity on BSC. It was the follow-up work of Forney due to Zablo, which showed that Forney's concatenation also leads to good codes. That's what we saw last time. But this It's precisely to answer, get the Shannon capacity was why Forney discovered concatenation. So what's the question over here? So let's recap. BSC, the BSC P channel. What's the BSC P channel? It's a binary symmetric channel. You have this, the input is 0, 1, which gets flipped. A 0 gets flipped to 1, possibly with probability P, and remains unaltered with probability P. Similarly, a 1 gets flipped with probability P and remains unaltered otherwise. So you have this channel, and the bits are going to get, the bits gets flipped independently. So we are now going to, and we want to recover, and the goal is to design a code, more precisely an explicit code. Shannon already gave a randomized code. So the goal is to design an explicit code that achieves the Shannon capacity. So that's the goal. We've already answered this question. We showed that there was a code. The only thing which we did not answer early on was we did not give an explicit code that did this property. And furthermore, both the encoding and the decoding, it was non-explicit in several senses of the word. The encoding was not explicit. The decoding was not explicit. The only thing that was very nice about that code was we got exponentially small error. The encoding, decoding, were neither of them were explicit when we did the Shannon codes, but the error, the probability of error was exponentially small. So what we'll now see is we will come up with a code. We'll see quickly, just now see that actually that analysis could be strengthened, and we can get a code which is explicit, but will have inverse polynomial error. So let's recall, what did Shannon prove? Shannon proved the following. Shannon proved if you pick a random code, of rate r equals 1 minus hp minus delta, will achieve capacity and furthermore the decoding that runs in exponential and n time has error at most 2 power minus delta n. So this is what we had proved of Shannon. What's the good features about this particular code was the fact that the decoding error is exponentially small. And the bad aspects of this code are the fact that the encoding and decoding are an exponential in n time. Okay. So let's try to redeem this. And so first thing I want to do is I want to redeem this aspect of it. I want to get codes whose encoding and decoding times are polynomial. Okay. Now notice that already in Shannon, we could have done something in Shannon. Shannon's code was this. If you recall, Shannon's code was this. He took n string long messages, and this was n, and he showed he constructed a random code on this length. What we could do is we could do his same construction but on log n length. Split this code up into n by log n blocks of log n length each. And apply Shannon's theorem on each block. We could have done this to this one. Notice that now we have a single code of length log n, which we are going to repeat along each of this ones. So the encoding becomes, what's the encoding time? Both the encoding and decoding for this object, encoding and decoding, are n by log n times xpin log n. The whole thing comes to polynomial n, which is a good feature about this code. Okay, that's it. That's with respect to encoding. Now let's ask the question about what's the decoding. Let's ask what's the decoding error of this code. Notice we haven't just used concatenation or anything, but let's just find out what's the decoding error of this object. Let's sort of, what is the probability that the ith block is decoded incorrectly? Notice this is exponential in its block length. So its exponential is minus log n. That's so it is 1 over poly n. This is, I'm just care about the ith block. But what we care that an error occurs. This is the same as probability. There exists some block I such that the ith block is decoded incorrectly. So I could just apply a union bound over here. This is n times log n times 1 over poly n. You choose the poly n to be larger than this, so you can get this to be 1 over poly n. Are people with me so far? I've done nothing so far. I haven't used concatenated codes. I just went back to Shannon's proof. Shannon gave a construction that was for n bit long. I'm going to apply the same construction on each log n bit separately, and hence state that because of this, I get the advantage that the encoding is polynomial, but the decoding, this is okay. So it's, what I want to comment here is decoding is poly n. So at the cost of getting poly encoding and decoding, we have increased the decoding error to 1 over poly n. Previously, the decoding error was inverse exponentially, but it's now 1 over poly n. People with me so far? So the question which we want to ask now is, can we improve construction? To get back inverse exponential error. Okay. And the main result of Shannon of Forney over here is yes, using vanilla concatenation, vanilla decoding of concatenated. And this is due to 4. So, and once I say this, it should be clear. So what is Forney's construction? Forney's construction is the following. It's going to use an outer code of rate 1 minus epsilon and say length n, and which can recover from say gamma fraction of errors. And all that I want is gamma is some number small. All that we need is gamma is some number smaller than epsilon by 2, then this is achievable. We will work with some significantly smaller gamma than epsilon by 2. Okay, if you use the epsilon by 2, there is of course the Reed-Solomon code that will achieve this, but we will use any of this. Is this fine? Yeah. So we will take an outer code like this. This is potentially over a large aspect. So that's the outer code. Let's then do the inner code. The inner code will be, of course, what it will be Shan. This could be, for instance, the outer code. This guy could have been Reed-Solomon, for instance. The inner, we will use a code whose rate is say 1 minus HP minus epsilon. Its length is, block length is n. That's going to be the inner code. And which code will be used for this? We'll just use Shannon's code. Shannon's random code. But small n will be logarithmic in the final block length. Therefore, it will be okay for us to do this. So the composed code. The composed code is going to be of rate 1 minus epsilon times 1 minus HP minus epsilon. This is certainly greater than or equal to 1 minus HP minus 2 epsilon. Its block length is nn, and we are going to set n to be something like log of capital N, some constant times log of capital N. Therefore, it's going to be. Now, I'm just going to do the same this once as before. What's the probability that the ith block is decoded correctly? incorrectly rather. This is Shannon's guarantee. This is exponential in minus n. This is just, I'm just invoking Shannon's result for this. Okay. Now, when will this recovery work? Are people with me, or have I lost people? So once again, what are we doing here? Let's go back to this construct. Let's go back to this picture. So this is the output of after passing through the BSC channel. So the channel has, this is the BSC channel now for us. And we have passed through the BSC channel and we have got this received word. And we've sort of done Shannon's brute force decoding to do that at the inner level. We got done these. And we know that most of the time we are going to be correct. There's a small inverse polynomial fraction of guys which are possibly going to be incorrect. Now, as long as this polynomial fraction of guys which are incorrect is less than the unique decoding radius of the outer, we'll just be able to recover perfectly and go ahead. Is that fine with me? As long as all I want to claim over here if the number of blocks that are decoded incorrectly is less than epsilon n by 2, then the outer decoding will recover message correctly. Is this okay with all of you guys? This main observation. Is that okay?
Yes.
So what's the error? What's the final error? So the error will be the probability of error for the entire code is exactly the probability that the number of blocks decoded incorrectly is more than epsilon n by 2 in the inner level. Okay, but notice this out here, we know a block is decoded incorrectly with probability exponential in minus n. That's a very small quantity. Therefore, the expected fraction, so the expected fraction of blocks that I expect to decode incorrectly is n times, capital N times this fraction. That's the number of blocks I expect. And I'm asking, will that number become larger than this epsilon n by 2? This is sort of a Chernoff bound like this one, and you can check. This is just going to be Chernoff. This will be like, you can notice that this is exponential in x minus n, the whole power epsilon n by 2. This is, I'm applying a Chernoff like bound over here. So you're going to get something which is exponential in minus n and n, which is what we wanted. So that's the happy part of it, that finally the decoding error has reduced to 1 over exponential in n. That's the end of the story. This is Forney's construction. This was how Forney showed concatenation and vanilla decoding of concatenated codes is useful to achieve explicit codes that achieve Shannon capacity with inverse exponential error. It's an extremely simple construction. Both concatenation as a concept is a very fundamental concept. It's a fairly clean concept, and Forney used this to construct explicit codes which achieve Shannon capacity. I sort of slightly cheated and hand waved in the argument. These don't give you fully explicit codes. The encoding is slightly super polynomial because Reed-Solomon with Shannon's codes don't give you encoding times which run in time poly n. They actually run in time n to the power log n. You can use Zabler's construction and concatenated that with Shannon's and then get fully polynomial. But this detail is not needed. It's just doing what we did. I did something quickly hand waved and did it, but more or less this morally what I've shown you now constructs polynomial time encoders, decoders with and get the decoding error to be inverse exponential in the block length. So that's already the advantage of vanilla decoding. Okay, questions? Any questions so far? Questions?
There's a question on the chat.
It's on the chat. Okay. Can you actually because
what is capital N in terms of N? In small n.
What?
What is the relation between capital N and small n?
So capital N and small n. So you need to keep. So right now I have kept the relation completely open between the two. But in order to keep you need to choose small n and capital N such that the encoding and the decoding time both become polynomial. Now the decoding runs in time exponential in small n. That forces you to small n to be logarithmic in the final block length. Therefore, small n will always be something log of the final block length. Capital N will be the final block length divided by this logarithmic factor. So it will be almost similar to the previous construction. It will be almost similar to the previous one where we did not use concatenated over here, if you recall, which was this one. Here we had n by log n. It won't be log n. It won't be just log n. It will be some huge constant sitting over here. So the small n will be some, say, 10 log n or something. Capital N will be n, and then you will put 10. Yeah. Any further questions?
I have a question about the final error.
Sorry, I don't catch you.
Yeah, so I will get in the bound 2 to the capital N of the term. Or...
So see, you have to just be a little careful about the Chernoff over here. 1 second. Let me try to see if I can my Zoom. I can now join in. Okay. This is just, I'm going to hand wave this. This is just going to be you're asking basically this. Pavel, you're asking this question, no?
In Chernoff, shouldn't they explain the Chernoff square?
This is a question of whether you are doing multiplicative Chernoff or additive Chernoff. The question is whether you're doing multiplicative Chernoff or additive Chernoff, and if you see that, it will be this. I have not done any of these calculations correctly. Fully, what you will finally get will be the decoding error. The final decoding error will be exponential in minus n, where n is the block length, the final block length, and it will be exponential in 1 over epsilon. It will be exponential in 1 second. What does it give you? It will give you exponential in whatever I said. So it will be an exponential in. So it will be this. It will be this object. It will be this. It will be, there will be some polynomial n, epsilon to the c, n over here, and the runtime and the n and the encoding and decoding will be in poly n plus exponential in 1 over epsilon. I haven't shown you why it's exponential. If you look at the construction carefully, this will happen. Later on in the course, we will try to address if we can make this exponential 1 over epsilon to poly 1 over epsilon. We'll see this much later in the towards the fair end of the course. Okay. What I want to now do is I want to improve vanilla decoding. All the way to recover from, let's say, recover from more errors. That is, t is greater than or equal to td by 4, but still less than td by 2. Okay, that's the goal for the remaining 20 minutes or so. Okay. So I'm going to change topics now and ask how I can improve the vanilla decoding to recover even larger number of errors. Let's look at two extreme cases. Two extreme cases of dd by 2 errors. So now one case which I do is, say I take small d by 2 blocks and our small d by 2 blocks are changed to different inner code words. Change different inner code words by flipping, say, d locations, small d locations. So this is one sort of error. That is, the errors are happening very sort of chunky errors. They're happening concentrated. Whenever something is corrected, it goes and flips the smaller guy by d errors, not small d by 2, but small d errors. But because you're allowed to only capital dd by 2 errors, at most capital D by 2 blocks are flipped. What will happen in this case? And by the way, I'm going back to, so to get the context, I'm going back to inner decoding. So let's. So I'm sort of going to this setting. Copy. Yeah. So what will happen in this setting?
The outer decoder will accordingly.
The outer, so the inner will fail on these d by 2 blocks, but the outer can handle these errors of d by 2. So let me state this: it's less than d by 2 blocks of the outer are changed to. The inner will fail on these guys completely, but the outer, but despite this, the outer will be able to handle them completely. So here, inner decoder fails on these blocks fails on this block, but number of such blocks is less than d by 2, hence outer decoder performs well. Now let's do the other extreme case in which less than d blocks are have d by 2 flips in there. That was case 1. Yeah, what would you do in this setting?
The inner decoder will stay in
The inner decoder will work. Inner decoder will correct. The inner decoder works. So I have flipped d by 2. So there's no guarantee that the inner one will work. Okay. I have flipped d by 2. I haven't said over here, I haven't said less than d by 2. So the inner decoder on all of them could have failed. It could have given you a different code word. But can you still recover from it now?
So you're saying the other blocks have more than d by 2 flips or less than d by 2?
So just say exactly d by 2 flips on less than on capital D minus 1 blocks. I go ahead and make d by 2 flips. There's no guarantee that the inner will work on them, by the way, now, because they could be 2 closest code words for each of these guys. So the inner on all of these blocks could fail.
It can brute force its possibility.
No, but even at brute force, it will get 2 code words. How will it handle them?
Can you use some list decoding?
Sorry, I didn't get you.
Like even the inner code cannot decode like uniquely. It can produce some like small list of possible inner messages and then use the decoding of our code.
So one way is to handle using list decoding of the inner decode. You could do that. But what we will do is today we will not adopt the list decoding of inner. This will actually go into your problem set, how to use list decoding of the inner and the outer to handle it. We won't do it. But notice these guys. So the inner, not on the inner at these places is unsure of in these locations. That is how much it doesn't know whether these locations are correct or not. But this is something it realizes because the number of errors is d by 2. It's not something that it does not know. It realizes that the number of corruptions have been at least d by 2. Even in brute force search, you can realize this. So what the inner can say is these blocks, just don't trust them. Just erase these blocks completely. This is an information that the inner could give the concatenated decoder, and the concatenated decoder just ignores these blocks completely. There are at most capital D blocks that have been ignored, and erasure decoding of the outer can work, and the outer can recover the code word perfectly. Are people with me over here? That is, suppose the inner signals, oh, you cannot trust my decoding on these blocks. That's what the inner is going to signal the outer, the concatenated decoder. It says on these blocks, the error is close to d by 2. So you can't trust what I'm going to output because it could be as well another code word. And so then the outer decoder just goes off and erases these locations, these capital D minus 1 blocks completely off, and then says, I will now try to recover from it. But on the remaining, it knows it's correct. On these guys, it's erasure decoding. It can recover perfectly. People with me?
Yes.
So what I'm claiming is Observe in this case, in this particular setting, inner decoder would signal the outer decoder that these locations, that these blocks are not to be trusted. The outer decoder erases these blocks and decodes perfect. So what we want is some mechanism for the inner to be able to signal to the outer guy. This is my confidence level of the decoding process. So the new algorithm which we are going to come up is in which the inner is going to signal to the outer object that this is the confidence with which, this is how much you can trust my decoding. And the outer is going to use this information to decide whether to erase that location or not, and then it will go ahead and recover the whole thing. Okay. So what I want is what we want is now an outer decoder, an outer code that can handle both erasures and errors. Now, what I want to know, suppose the distance of the outer code was, d out. What's the number of erasures it can handle? I want to say can handle if number of erasures is less than d out. This we saw already. That is, even if you erase these guys, you will be able to recover from the code word. And it can also handle if number of errors is less than d out by 2. Now I want to ask, suppose you have a mixture of erasures and this one, what can you do? I want to ask, can it handle yes erasures and e errors? So far we handled only one of the two. Either they are erasures or there are errors. And I want to claim actually you have a very nice this one, as long can handle if s plus 2e is less than d out.
So in the third bullet point, you saying there are either S errors or E errors, not quoted the same.
So the first two are either, first case is there are the number of erasures is d out. The number of erasures is e is yes is less than d out and there are no errors. The second case which I said was the number of errors is d out by 2 and there are no erasures. Now I'm asking a combined thing in which there are both erasures and errors.
But
and I want.
Doesn't the inner decoder do this? It says if it's confident that it has decoded correctly, then it will give the correct bit. But otherwise it realizes that.
No, Srijato, let's not jump ahead. Let's not go to the concatenated code. I'm just asking outer decoder. I'm giving you a decoder and I'm asking you how many erasures and how many errors can be handled. Let's just ask that question first. Let's answer that question first. I want to prove this claim. I want to prove this here, this claim. And I want to know if you guys believe this claim. That is, suppose I give you a code word and I make S erasures and E errors. Can I recover from this? So once again, let's look at this. What happens? I want to claim you can. So suppose I give you a code C, which is an NKD over some alphabet code. Now I apply the S erasures. At the end of it, I'm going to get an N minus S. Those S locations have been disappeared. Possibly the whole K is there. I don't know about this. And this one, possibly I lost distance D minus S. This is what I should be having. But I know now, this is the new code I have. On the non-erase locations, I have a code of block length N minus S with distance D minus S. And this is a code. If it has distance D minus S, this code I can recover from D minus S by 2 errors. So this is a new code C prime. Can recover C prime from E errors if E is less than D minus S by 2. And that was the end of story. That's what we were. That is 2E plus S is less than D. So all I want to claim is if any code you must be able to recover if the erasures, if the number of twice the number of erasures plus the number of errors is less than distance, you can recover. Is this okay? Are people with me or have I lost folks?
Yeah.
So the usual decode, any code, you can decode up to the unique decoding ranges, which is the distance by 2. But now I want to say, no, I'm allowing 2 types of corruptions. One is erasures, one is errors. There are going to be some erasures. Erasures, you know that these are erasures. Corruptions, you do not, errors, you don't know these are errors, corruptions. But as long as you have a bound on both of them, what is the uniform bound I have? Twice the number of erasures. Sorry, twice the number of errors plus the number of erasures. As long as this number is less than D, then we can recover. And the proof of it is just what I have said so far. By the way, this proof is combinatorial. I haven't said algorithmically how to deal with this proof. Right now, I say every code one should be able to recover from S erasures and E errors if S plus 2E is less than D out. What about, now the next question will be, what about algorithmically? Are the questions clear to me? Firstly, one is stating that you can recover from so many erasures and so many errors that you should be able to. Other is you have an algorithm that recovers from. So it's not true that you always have an algorithm, but I want to claim if the outer code is Reed-Solomon, then we can do this, because what does it mean? Reed-Solomon, it didn't matter to you the set of when you erase locations, you are dropping off certain locations, evaluations, and now and the new code is still a Reed-Solomon code. It's a Reed-Solomon code on a smaller set of evaluation points. So Berlekamp-Welch algorithm never cared about what were the set of evaluation points. For every set of evaluation points, you could apply the decoding process. The Reed-Solomon decoding, which we saw a few lectures ago, had this property. And hence, the Reed-Solomon code, the Berlekamp-Welch decoder the Welsh-Berlekamp decoder can handle this. Since the algorithm worked for any set of evaluation points. On the other hand, suppose I had given a decoding algorithm that worked only when the set of evaluation points was F and not any smaller subset. Then this would not have worked, because when you erase it, you are dropping it off and I don't know how to handle it. The point was the Welsh-Berlekamp algorithm did not use the structure of the evaluation points. It worked for every set of evaluation points. It managed to get it. Are people with me or have I lost folks? Somebody had a question?
Yes, so in a concatenated code, can it be the case that there are D blocks, capital D blocks, and there are D by 2 plus 1 flips in each.
Srijato, let's defer concatenated questions later. I'm asking firstly, you've just followed this particular thing. I'll come to concatenated in a second from now, but I want to ask this particular question regarding this one. Is this fine right now? Okay, if this is fine for everybody, this one, now let's go. Okay, now ask the question on concatenated codes. Yeah.
So if there are capital D blocks, and
Yeah.
there are D by 2 plus 1 bit flips in each, around D by 2 plus 1 bit flips in each blocks.
Yes.
And on the outer decoders, there are around capital D bit flips and no erasers.
No, but if there are small d by 2 plus 1 flips, this is more than the number of errors that you can allow for. This is not a setting which I can promise that I can recover from at all.
Yes, so let's say 3 capital D by 4 blocks, and on each block there are small d by 2 plus 1 errors.
Yes.
And then you will see then the outer decoder only see there are more than capital D by 2 errors, and he does not know.
Yeah, so we have to handle it's a very valid case. We have to handle that. Question is, how do I handle that? And the algorithm I'm going to give you now is going to handle that. I didn't give you the algorithm yet. So I'm going to give you the algorithm now. So now let's talk about Forney. Subsequent to his previous work, he gave this new algorithm, Forney's GMD decoder. GMD stands for Generalized Minimum Distance Decoder. So what I will do is I will state the decoder and then we'll defer the analysis to next lecture. And the input to it will be the requirements for it. So this one will be C out, an outer code with a decoder D out that can handle E errors. So let's call this decoder out that can handle E errors and S erasures if 2E plus S is less than D out, and inner code C with distance D in and a decoder tech in, that can handle F errors if 2F is less than P. This, then Forney will, then GMD decoder give you for the compose code. What we're going to give is for the compose code a decoder, if we call the G decoder, that can handle anything less than D out by D in by 2 errors. Okay. And the algorithm is going to go, so the GMD algorithm. So this is what I'm going to promise you. I'm going to give you a, Forney is going to give such a decoder in which if the outer decoder is some outer code and comes with a decoder that can handle both erasures and errors up to the distance. Basically, as long as the number, twice the number of errors plus the number of erasures is less than D over 2, the decoder can handle it. And the inner decoder is some inner code that can handle errors all the way up to half the minimum distance of the inner code word. Suppose you had decoders for both the inner and the outer which satisfied this process. Forney is going to give a GMD decoder which can for the concatenated code, it's going to handle errors all the way up to D out into D in by 2. This was not something which the vanilla decoder did in the past. Questions before we write down the analysis, write down the explicit decoder? Questions about what this means? Somebody was asking something. No questions? Okay, so let's write down the algorithm for the GMD decoder. What's its input? Its input is this R11, R1N, that's the first block, R21, R2N, that's the second block, and so on, RN1, RNN, that's the receiver. So the algorithm. So for each, so it's first going to run the inner decoder. For each I in N, it's going to run the inner code of run the decoder inner to obtain, run the decoder inner on RI1, RIN to obtain, say, ZI. Okay, that's the inner decoder I'm going to output. But I'm going to do one more step. I'm going to that's what you would have done all the time. But I'm going to do one more step. We are going to find out EI, which is the distance between the encoding of ZI and this RI block. Notice that if the number of sometimes this will obtain ZI or bottom. It's going to obtain either a ZI or a bottom. It's sometimes going to say I can't decode because the number of errors is more than D by 2. I don't see any code word in the D by 2 ball around this location. Let EI. Technically, EI is not going to be just this. It's going to be minimum of this and D by 2. So if it's what, I'm just going to define it to be d by 2. Now, what I'm now going to do is, with probability EI by d by 2, erase Zi. Otherwise, retain Zi. Now, I'm now going to say, now you have this. What I want to claim. Now you have this Z1, Z2, Zn, some of which are erased. So, run outer decoder, deck out on Z1, Z2, Zn to obtain M1 tilde, M2 tilde, Mk tilde. That's the end of it. Okay. So this is the way I have stated it, it's a randomized algorithm. So what does it do? We'll defer the analysis to next time. I don't have the time for the analysis, but let's see what the algorithm is doing. So it's going ahead. It's going to go as before, run the inner on each of the inner blocks first. So it's going to run, if you go to this algorithm, it's going to run the inner object on each of these blocks. Okay. But then it's going to look at the recovered object. It's going to ask what is its distance from this guy. If the distance is very close to d by 2, it says its confidence is very little in the code word, and it's going to erase it completely. Therefore, it's going to do this sort of, it's going to come up with this some confidence metric on it. It's going to look at this number, the number of the distance between the recovered, the decoded location and what was there in it. It's going to divide that by d by 2. And if this quantity is closer to 1, it's going to erase that location completely. The closer it is to 0, it's going to retain it. So it's going to do one of these two based on this one. And it has now a n symbol thing, some of which have been erasures. And now we are going to run the outer decoder on this object. And the claim is this one works well. This is a randomized algorithm. First, we will see an analysis for this algorithm in next lecture, and then see that actually it doesn't require randomness. They can remove the randomness also. This is going to be Forney's GMD decoder. So first question I want to ask is, we will do the analysis next time, but I want to ask, is the algorithm clear?
Yeah.
So it uses this clever idea. It's going to come up with a confidence metric about how much the inner decoder you can trust. And using that confidence metric, it throws a random point based on that confidence metric, and then decides to erase or a location or not, and then going to run the entire algorithm. Srijat, now does this answer your question?
Yes.
Yeah. So this is going to be the concatenated decoder. It's going to sort of do this. It's sort of interpolating between the two extreme cases that we talked about. In one case, you didn't have to erase anything. The other case, you had to erase a lot of things. And this is sort of going to do the two intermediate. It's sort of interpolating between the two cases. This is the GMD decoder, Forney's GMD decoder. We'll analyze this in the next lecture, and we'll also show how the randomness can be completely removed from this. Any questions on the algorithm? We'll defer the analysis to next lecture. So we'll recall the algorithm and do the analysis in the next lecture. Okay, then we'll break now. By the way, the second problem set will be out at the end of the day. It's ready. I just had the individual breakup of points. It will be ready by the end of the day. We will not have lecture on Wednesday. Our next lecture will be on Monday. Okay, where we'll continue with the GMD analysis. Yeah, we can stop recording now.